name is Melvyn, and today I will be presenting my master's thesis, which is developing a smartphone-based travel diary tool. So the overview of my thesis, I'll be talking about first GPS data and how it's related to mobility insights. I'm going to talk about Google Maps and the Google location history, which is the data that the app will be collecting. Then I'll be talking about the Tracy survey platform and the KML offload module, which will accept these KML Google location history files. Then I'll talk about the survey that we have performed using this tool, the Google Timeline Travel Survey, and I will show some sample data statistics from the survey. Afterwards, I will talk about the analysis of this data, such as making a validation model for the Google mode choice inferences, and also comparing between the TTS and the GTTS data. So to start off, mobility data is very important, of course. It drives all transportation analysis, and it is present in all factors of civil engineering. And the primary collection method for this travel data is travel diaries. So there's two main methods right now. There are web surveys, traditional web surveys where respondents will log down their own travel patterns from their memory, but this leads to some issues such as biases, underreporting, and recall errors. We also have GPS surveys where every respondent's trips are automatically logged for them through GPS, but some barriers to this technology include recruitment barriers and also installation barriers and issues with proprietary software and cost. So this is where Google Maps and Google location history comes in. Since Google Maps is very widely used, it's installed in basically all smartphones. Pretty much everyone has access to Google Maps. As well, there is no charge for this app, and the Google location history built into Google Maps features comprehensive real-time route and location tracking. And also it automatically stores respondents' trip patterns in the background, so they don't have to launch a special app or anything. All of this location history data is exportable in a format called Keyhole Markup language, which is a geographic data format. So here's a look into an example KML file. So each file records a sequential record of the respondents' activities and trips, and there are two types of events in these KML files. There are trips and activities. And for each of these events, it contains specific details such as the time, the duration, the coordinate traces, as well as addresses, inferred travel modes, and land uses for the destinations. So, how do we collect this Google location history data? As I said, when enabled, Google Maps passively collects this history data, and respondents can log into their Google account to download this data. However, just asking for respondents to upload these raw KML files is not very effective because we still need them to validate each mode and to check if the inference is correct. So with that being said, we need an efficient method to collect this Google location data as well as their respondents' validations. This is where the Tracy survey platform comes into play. It is a multi-platform, intuitive, easy to use for respondents, and also for survey administrators. It allows for very easy survey construction, and it is very modifiable because any new modules that need to be created can be created. So the Tracy KML upload module is one such module that was created in Tracy. It accepts these Google location history KML files. It generates a travel diary skeleton that the respondent can then fill out with the drop-down menu. Using these menus, they can validate trip purposes, they can validate activity purposes and trip modes. So after they have validated these events, the module saves each each option that the respondent chooses into the KML files and annotates them, which we can then download from the survey database. After the annotated KML files have been downloaded, we process the files and split them into separate activities and trip legs. And then afterwards, the trip legs are joined back into either single mode trips or multimodal trips. So, with all of these tools in place, we developed a Google Timeline Travel Survey, which is a two-phase survey that will ask respondents for their KML files and ask them to validate it. So during the first phase, we asked the respondents to set up their Google location services if it wasn't set up before, and we also collect some basic socioeconomic data. After we allow them to collect some travel data for a week or two, we follow up with phase 2 of the survey, which will ask them to upload these KML files and annotate them using our upload tool. So 2 cycles of this GTTS survey have been completed. The first cycle was spring 2023 from May to July. The sample source was a market research panel, and around 57,000 invitations were sent out. The response rate was around 1.53%, and the completion rate was 33%. Compensation was $2 for the completion of phase 1, and if they completed phase 2, there was a further $10. The second cycle that we administered for the GTTS was done during fall 2023, during October and November. Now, the sample source for this one was the email list of previous TTS respondents, 2022 TTS respondents to be exact. And we sent out around 32,000 invitations. We got a response rate of around 2.62%, and the completion rate was 63.7%. The compensation for this survey was a bit different. It was just a flat $20 if they completed both phases. So now I would go into some sample statistics from the data sets collected from these 2 cycles. So for the spring GTTS, 879 respondents replied for phase 1, and 188 respondents completed the whole survey for phase 2. In the end, we collected 4,116 total trips at 7 days per person, and 3,808 of these trips were single mode trips, and 308 were multimodal, which equals to a trips per day per person of around 3.09. For comparison, the 2022 TTS primary respondent trip rate was around 2.77. The proxy respondent trip rate was 2.13, and the combined rate was 2.43. Also, the 2021 fall COVID rate, which was a survey done to look at the effects of the pandemic on travel, the rate found there was 1, which we can see was affected by the pandemic. So for the spring data set gender distribution, we will be comparing the statistics to the census, the 2021 census. We can see that in the spring data set, the sample is a little bit skewed towards women. For the age distribution, we can see that most of the respondents fall between the ages for working adults, so between 30 and 64. And then for the employment types, there is a much larger representation of full-time employees in our spring GTS dataset. For the workplace arrangements, we can see that most people worked exclusively from outside home, but there actually is an even split of people who work from home only and people who are in a hybrid arrangement. For the income distribution, it actually matches the 2021 census distribution pretty well, except for the higher end, for the bracket 200,000 and above. Here's just a rough plot of all of the household locations of the respondents. You can see they are mainly centered in the GTA area, and there are a few outliers here and there. For the actual mode share, you can see the majority of trips, around 69%, are made with automobile. There is a pretty large portion of trips, however, that are walk trips, 17.2%, and the next largest mode is local transit with 7.9%. Moving on to the fall GTTS dataset. For this survey, we had 678 respondents who completed the survey in total, and all these respondents, we collected 17,654 total trips. Of these trips, 16,151 were single mode trips, and 1,504 were multimodal trips. This equates to a trips per day per person of around 3.29. And also as a comparison, like before, you can see the TTS response rates. Moving on to the gender distribution for the fall data set. You can see it's the opposite of the spring data set, where this one is skewed towards male respondents. For the age distribution, we can see a very similar pattern, where the respondents were mostly adults aged between 30 and 64. As for the employment type, the fall data set actually has a larger portion of respondents who were full-time employees, and a much smaller portion of employees who were employed part-time. As for workplace arrangements, the workplace arrangements were actually drastically different from the spring data set. As you can see here, the majority of, actually more than half of respondents actually worked in a hybrid arrangement. So half of the time, so like some of the time they would be telecommuting, and the full-time and work from home only portions of the respondents is much lower than the spring data set. For the income distribution, we can also see differences from the fall data set compared to the spring data set. In the fall data set, actually, there is a much higher representation of higher income households, such as households above 80,000, 125,000, and 200,000. And here is another geographic plot of the respondents' household locations. This one has much less outliers. Most of them are located in the Greater Toronto area, which makes sense because this is from the TTS email list. As for the trip mode shares, we can see very similar patterns here, similar to the spring GTTS, except the walking portion of the mode share is actually a little bit larger, 22%. So we can also compare the trip distance and durations for the spring and fall data sets. You can see here, both data sets actually follow a pretty similar distribution for distance and duration, with the fall data set having trips that are a little bit shorter and a little bit lower duration on average. As for each individual mode, here we have the auto comparison. For automobiles, the distributions of the distances and durations were very closely matched. However, for the transit trips, we can see that the fall distributions are skewed, noticeably skewed towards shorter trips. We can also see a little bit of the same thing here with the walk trips, where the durations of walk trips during the fall are skewed a little bit towards shorter trips. And for the cycle trips, they are fairly well matched for the spring and fall. Moving on to the analysis of these data sets. The first analysis we did was a Google mode inference validation. So for each KML file and for each trip event in these KML files, Google provides a mode choice inference. This is a black box. We don't know what algorithm Google uses and what input characteristics they look at to determine the mode choice. So the question is, how accurate are these inferences when compared to the user-validated modes? To start off, we created a confusion matrix for this, for the Google inferences and the respondent validations, and we can see that actually the recall and precision of each mode is fairly accurate for Google. We can see some of the lesser known modes, lesser used modes, less common modes are a bit less accurate, such as motorcycle, taxi, and ride hailing. So to actually test the accuracy of the Google inferences, we developed a binary logic model. The independent variable was the probability that the Google inferred mode is incorrect. And the inputs would be the trip maker socioeconomic variables as well as various trip characteristics. And this is the final binary logic model specification. The pseudo-rho square was 0.43, and you can see all the coefficients and t-statistics here. As for the actual characteristics we include in the model, it's things such as the average speed of the trip, the average distance, also the land use characteristics of the trip origin, as well as trip maker characteristics such as the age, whether they are a full-time worker or not. So looking at the final coefficients, we can see the Google mode inference is less accurate occurring several factors, such as when the trip has a lower average speed, when the origin has a higher density, population density, when the trip maker is younger, and when the trip maker is a non-full-time worker. Moving on to the next bit of analysis. For the fall cycle of the GTS, since the respondents were recruited by the TTS email list, technically you can consider the GTS as a satellite of the TTS survey. This allows direct comparisons between individual TTS respondents and their GTTS data. So, which means we can actually match up the trips, the traditionally reported trips of the TTS respondent compared to their GPS recorded trips on the GTTS. So plotting down the trip rate difference between these two data sets, we can see that the naive differences between the trip rates are actually distributed around 0. So we have two differences here. The naive single-day trip rate difference, which compared the specific day of the TTS to the GTTS day. And we have the 7-day trip rate difference, which compares the TTS trip rate to the average, 7-day average of the respondent in the GTTS. However, this naive comparison does not account for the distribution of weekdays in the TTS. What that means is, in the TTS, the respondents didn't actually respond uniformly over every single weekday. Some weekdays had more observation than others. We can see here that more respondents filled out the TTS on Thursdays and Fridays, and the day with the lowest observations is Monday. So to account for this, we applied some weighting factors to the trip rates depending on which days they were reported on. So trips from days that we had more observations for would be weighted less. So after applying this weighting to these distributions, they actually didn't change the shape of the distributions dramatically. They were still had a mean around 0, and they were pretty evenly distributed. So with this in mind, we can see that the difference between the TTS and GTS trip rates do not really skew towards underreporting or overreporting. So as well, both surveys found that the average trip rate between matched individuals were pretty similar. For the TTS, it was 3.08, and for the GTS, it was 3.29. As the KML data for the GTS was not collected simultaneously with the TTS, because the TTS data was collected fall of 2022 and the GTS was collected fall of 2023, there is a year difference between these data sets, so it may account for some of these differences, but we can conclude that the TTS and GTS are pretty well matched. The TTS respondents do have a reasonable level of accuracy when compared to the GPS recorded trips of the GTTS. So the next step for the comparison of these data sets, the subset of the TTS respondents who actually didn't reply to the GTTS have pretty different trip rates. We can see that the TTS respondents who chose not to complete the GTTS had an average trip rate of 2.76, and the proxy respondents for the TTS had a much lower trip rate of around 2.13%. So with that being said, with these differences in trip rates between these different subsets of the TTS, we should check for if they contain any significant underreporting or overreporting. So we can develop a matching scheme for the TTS respondents who did not reply to the GTTS, and we can match them up with the similar GTTS respondents based on socioeconomic variables, household variables. And after we have matched them up, we can try to find a method to correct these biases and errors in these non-GTTS respondents and proxy respondents. So in conclusion, we found that Google location history and the KML files that describe this history is a good source of transportation information. It is very easy to set up for respondents. It is low impact. They don't have to do anything special, such as downloading an app or having an app in the background to access this data. And also the data from these KML files are very rich and in-depth. So with the custom-built travel diary module, we also found that the KML files are pretty easily parsable and they are very straightforward to work with. So some possible improvements for this survey would be to try to increase the response rate, which would entail enhancing the user friendliness, perhaps streamlining the survey process and providing more detailed information on how to set up this Google location history. For the analysis, to recap, we found that the Google location history mode inference was pretty accurate for the common modes, but a little bit less accurate for uncommon modes that have lower volumes. For the comparison between the TTS and GTTS, we can see that the subset of TTS respondents who answered the GTTS had pretty accurate trips in the TTS. However, for the non-GTTS, TTS respondents and the proxy respondents, their trip rates are significantly lower. So the next step would be to investigate the reasons to this and how to correct this. And that is my presentation. Thank you for listening.